The ancient Greeks came up with the theory that everything in the world was made up of tiny, unseen particles called atoms. And for centuries, it was assumed that the atom was the fundamental particle, the basic Lego building block of matter. But then, at the end of the 19th century, scientists began to probe and explore what might be inside the atom. And they found that it was made up of bits and pieces that we all know about, protons and neutrons and electrons. But then they found these components were themselves made up of vastly smaller particles still. And then it was discovered that the whole planet is constantly being bathed in subatomic particles from outer space. Yes, really, that's happening all the time. Suzie Sheehy is here. Suzie is an Australian physicist who divides her time between Oxford and Melbourne universities. Suzie's specialty is accelerator particle physics, a branch of physics that uses some of the biggest machines in the world, like the Large Hadron Collider, which takes up half of Switzerland, to manipulate the tiniest objects in the universe that we know of, the infinitesimally small particles that make up everything, planets, suns and galaxies and water and earth and trees and humans and cats and dogs. Suzie Sheehy has written a book that charts the quest to find out what matter is truly made of, and it's a bit like a tour right down to the basement of reality. Only it may well be that there is no basement. Suzie Sheehy's book is called The Matter of Everything, 12 Experiments That Changed Our World. Hi, Suzie.
Hi, thanks for having me.
So we get to the end of the 19th century. The universe is in a nice, orderly place. We think we've got it all figured out. You wrote that it was even thought that they were getting pretty close to the end of physics. They were just about to nut the whole thing out, and then you physicists can go off and, I don't know, play backgammon or something. I don't know.
Right. Physics was over as far as a lot of them were concerned. You know, that fundamental level, all done. We knew that we had atoms. We knew that light was made of electromagnetic waves. We had the theories for those. It was great. We could predict things with it. And it was thought that the universe was kind of predictable and easy to put together if you had enough sort of brain power or calculation power. So I could tell you the positions and directions of movement of every single particle or atom in the universe. And from there, technically, if I was clever enough, I could tell you how that would evolve for all of time. And even some of the key figures who come out in my book of what happened next were told early in their careers, no, don't study physics. That's done. There's nothing new to be found there. It's just, the only interest is in like the last decimal place, 15 decimal places. Right,
so the outline had been drawn and it was all just colouring in.
Exactly, and who wants to do that for their career?
No.
That's where physics was at. They thought it was known, except for the bits that weren't.
So then you have this guy, Röntgen, who comes along, this German scientist called Röntgen, and he ruins everything. Tell me about the experiment he conducted. He actually managed to accidentally, really, smash up this cosy picture of what the universe was like.
Right. Well, he was one of a handful of scientists working around the world who still thought there was interesting things to be doing in physics. Wilhelm Röntgen Wilhelm is his first name. He's working in Würzburg in Germany, and I've been there. I've been to his lab that he was working at the time. It's beautiful. It has parquet floors and lots of light flooding in. I've taken inspiration from my new lab. And what he was working with was a device called a cathode ray tube, which...
Like a TV?
Similar, or like the early phase of those devices. It's a glass tube with all the air taken out, and it has an electrode at the start from which, we now know electrons come out of that. But in those days, it was one of the few instruments they didn't understand fully how it worked, because it would create this sort of greenish glow inside the tube. And so he and a number of other physicists around the world were working with this, trying to understand exactly what was happening. How did this glass tube create this glowing light? And he had one in his lab, and he was playing with it one day, and noticed over the side of his lab there was a fluorescent screen glowing, completely separate from the device that he was working with. Now, a lot of people would have just been like, oh, I don't know, there must be the light from the window coming through or something, and would have ignored it, right? But Röntgen was fascinated by this, and he thought, I wonder if that's something that's happening from the tube in front of me. So he switched the tube off again, because it's controlled by a power source, and the light on the screen went away. And he switched it back on, came back again. He thought, oh my goodness, something is emanating outside of the tube and lighting up this screen, but it's invisible, I can't see it. And so he does a series of experiments where he covered up the cathode ray tube, first of all, with like a cardboard box, and then he put things between the cathode ray tube and the screen. So he tried rubber, he tried metal, he tried books and blocks of wood. He put it through the door to the next bit of the lab, and he eventually figured out that whatever this thing was coming out of the tube, it could go easily through light materials like paper, but it didn't travel so easily through heavy materials like metal. And that gave him an idea. So he put his hand in the way of the tube. And then he saw on the screen the outline, not just of his hand, but of the bones inside his hand.
Far out. Far out. That must have been a bit of a mind-rattling moment when he saw that.
Well, I guess he thought, is this real? Someone else has to see this. Because the next thing he does is he calls his wife, Anna Bertha, in, who'd been providing him with food as he did this investigation. He was 7 weeks in the lab. He barely left. And so he insisted that she come down, and she put her hand in front of it, and he took a photograph then of her hand using these rays, which we now call X-rays. And so she could see the bones and inside of her hand and the dense ring of her wedding ring, but the skin and the flesh, the X-rays could travel through quite easily. And she responded by saying, "I have seen my death," and she never went back in his lab ever again.
Well, there is something creepy about seeing X-rays. Even today, where you look at them, you go, I shouldn't be looking at that. There's some violation.
For the first time ever, we've at least seen images of X-rays in popular culture, right, even if we haven't had one ourselves. But to be able to see inside the body for the first time must have been so surreal.
So why did this suddenly disrupt this comfy model of science and physics that had been in place up until he realised that there was these things called X-rays actually existed?
So his was one of the experiments that did that, because suddenly he had to understand, well, what is the nature of these X-rays? Are they light? Are they some other form of radiation we've never seen? And so he had to do a series of experiments to try and figure that out, because they didn't quite behave like normal light, but almost. And they turn out to be, now we know, a high energy form of light, but they're not visible to us, and they can travel through things in a way that visible light can't do. So they're slightly different. But this tube, and understanding how the X-rays were formed in the tube, then kicked off a series of other experiments, including ones by J.J. Thomson in the UK in the Cavendish lab in Cambridge, to try and understand not just how it was generating X-rays, but still what was happening inside the tube. And Thomson ends up doing a series of experiments using magnets and electricity to bend this rays around inside the tube now. And from that, he managed to establish that the rays, the cathode rays, this glowing green thing inside the tube, was not light inside the tube. It was actually made of tiny fundamental particles 2,000 times lighter than the lightest atom they'd ever seen, which was hydrogen, and that they were negatively charged, and that they seemed to be a component of all of matter. It didn't matter what he did in the experiment to change the source of these particles.
So they couldn't be atoms themselves. They were particles that were far smaller than atoms,
right,
and negatively charged.
Because they'd never seen an atom that small or that light. The only other possibility would be if that atom had a very, very large electric charge, but he managed to rule that out based on some other evidence.
So we're talking about electrons here, essentially.
Exactly. The first subatomic particle, the discovery of the electron, and that's 1897. That's just about 1.5 years after Röntgen discovers X-rays. So suddenly this tube that everybody has in their lab, there's hundreds of these things around the world, suddenly becomes the focus of attention, because and people had been doing experiments with them for quite a while, trying to understand what was happening. And so there were small pieces being put together, but really Röntgen and Thomson were the ones who finally sort of made that final step in the standing on shoulders of giants, which meant that they could pull together all of that knowledge and go, this is now unequivocal. There is a particle smaller than an atom.
So the atom is not a fundamental particle. It's not the absolute rock bottom building block of reality. So this begins this kind of journey that takes place and is still going on now down an elevator, if you like, or through a microscope, which gets smaller and smaller and smaller as we keep trying to find this fundamental particle, this tiny, tiny, tiny thing that might be at the end of a process here or not. How did you become involved with all this, Suzie? How did this begin with you? Because you started at uni in Melbourne doing civil engineering.
Yes.
So why aren't you making box girder bridges? What turned you away from that? Why are you looking into the nature of matter and reality now?
Yeah, so a couple of years into, or sort of at the end of my first year of university, I'd been studying physics alongside engineering, I guess as like a sort of backup, right, to sort of make sure I understood the fundamentals well. And I had a couple of quite inspiring lecturers, but I'd also met some friends through my physics classes, and we went away one summer with a bunch of telescopes observing the night sky. They do this annual camp called astronomy camp, and I, being the nerd that I was, I went away on this camp because it sounded fun, and I just remember I was lying there, in a sleeping bag, but just lying there looking up at the night sky in this beautiful location called the Leon Mao Dark Sky Site, which is just outside, a couple of hours outside of Melbourne. And there's no light pollution around intentionally. That's why it's a dark sky site. And so the night sky there is absolutely beautiful. And now talking to Australians, they understand how gorgeous our night sky is because we actually look into the centre of our galaxy, the Milky Way. So there's this bright band of stars across the centre of our sky that Northern Hemisphere folk don't get.
Yeah, we have a dress circle seat, don't we, for the Milky Way? Yeah, that's great. I've seen it from that kind of night sky in outback Queensland.
Yes.
And it's stunning. Like it's just gigantic. It's like you can't ignore it. There's nothing going on the ground. There's no one around because it's completely empty. But there's this riotous thing going on just over your head.
It's quite life-changing, isn't it?
Yeah, it is.
When you really see it.
Yeah.
That was really the first time that I'd taken the time to also let my eyes adjust as well, because it takes about 20 minutes for your eyes to see the full extent of the light that they're taking in. So I do, like, if people go out camping, all the lights off, get your phone torches off, everything off, and lie there. And, no fires. Okay, it's gonna be cold, but take 20 minutes before you do all that stuff because the sky just looks absolutely spectacular. And it was from that moment where I sort of realised that perspective shift of me being this tiny human on this big ball of rock travelling, around this. Around our sun, and then that being just one star in our galaxy, and then everything else that was out there. And just me thinking, look, any other line of work has me focusing on this tiny corner of our universe which we live in. Whereas physics, by understanding cosmology and dark matter and black holes and particle physics and all these things, I thought, well, that gives me a chance at least of understanding all of that out there, which suddenly I realised was important to me.
Yeah. There's two ways of feeling about this. There's that beautifully humbling moment, as you say, when you realise you are the tiniest speck on a tiny speck, which is part of our galaxy, which is one of a bazillion other galaxies, and it's a feeling of being the tiniest thing in the universe. But on the other hand, you can turn that entirely on its head and say, given that there is no centre really, there's no real fixed point in the universe as such, you're at the centre of that universe pretty much. I mean, we all are at the centre of our own universes right now. Yeah, we've got rival centres of the universe going on, even in this room right now. So this leads you on the quest to sort of look into the nature of matter itself.
Yes. So I guess I started thinking astronomy and astrophysics was beautiful, and then my brain went, okay, but fundamentally it's built up from these individual particles. Somehow we get from the early stages of the universe where these particles start sort of forming, and then we get to this immense complexity that we have now. And I thought, well, that all comes down to whatever is the most fundamental thing in the universe and the forces that operate between them. And so that led me down the path of trying to understand the field of particle physics. And originally, in my undergraduate days, I did a little tiny bit of research on the ATLAS detector, which is one of the 4 big detectors at the Large Hadron Collider. And I was a very, very lucky Aussie student at that point, because I think I was one of the first to get to go to CERN for a 3-month period to do a summer project.
That's very cool.
So I actually got to see the Large Hadron Collider when it was being built. And that was an enormous inspiration. And I have to tell you the name of the project that I worked on at CERN, because it puts in perspective my role as a student on that enormous collaboration. And it was the monitoring system for the heaters, for the cooling system, for the inner detector of the ATLAS detector at the Large Hadron Collider.
How could you fit that on a business card, I wonder?
I know, right?
Right.
So, at some point, I realised it didn't matter how small the project was. It needed to be done in order for this enormous thing to be a success.
Again, there you are as a fly speck on this very large and vast enterprise that's going on all around you.
Exactly. I later shifted tack a little bit from using the big machinery to find out new things about the universe. And for my PhD and my research career now, and I lead research groups in this, I actually now design the particle accelerators themselves, both for big experiments like the Large Hadron Collider and also much, much smaller ones for more practical applications.
Well, then I feel like I'm entitled to ask you this question. Can you tell me what matter is in a way that's not circular? What is matter? Do we even know what matter? I mean, because every time I keep arriving with what I think is the definition of it, scientists go, well, actually, it's not.
I think the answer will change depending on who you ask. And this is an important thing. And it's also, I think the answer would depending on which scale you're looking at and exactly why you're asking the question of it. I know this sounds like a roundabout way to go about it, but for me, if I ask, well, what is matter? In my day-to-day life, I can say, well, this table is made of matter. The particles, even in the experiments that I design, are matter particles, and I don't, on that scale, actually have to consider the fact that they're actually quantum in nature and have wave functions and aren't quite solid.
Is it something with weight? I mean, is that a good way to describe it? Something that drags a bit if you try to move it? Is that a good way of describing it?
So some matter has a mass. Yes.
Here we go.
That gravity can act upon. But then it's interesting, right? Because then we get to the point, well, what's the opposite of matter? Is it light? Is it energy? What's
antimatter?
Can you define? Well, that's true. Antimatter. So we can only really ever define things,
right,
as their juxtaposition to something else.
So really is the point then not to define things? I mean, does that just get in the way of the work you try to do?
We have really clear definitions in mathematical terms that we can use to calculate. But when you ask me a question like, what is matter? I'm sort of like, well, it depends who's asking and why they're asking. And because also it depends on, can I do an experiment that tells me definitively, is this thing in front of me made of matter? That's a very difficult question. And I have to get more precise with my questions. I have to say, well, does this object have mass? Does it have a certain quantum property called spin?
Yeah, but everything in the world's got fuzzy borders, and you can sort of speak in general terms about things, surely, can't you?
If I think, how would I define matter to someone who just doesn't, who doesn't want to study particle physics? I'd be like, well, it's probably the stuff with mass, right? But antimatter has mass too. So.
Okay, so we've had this situation now where Röntgen has stumbled onto the existence of things called electrons that's then been established by other scientists as well. At the same time, we've got Marie Curie and Pierre Curie in France, and they've discovered radioactivity. Yes. And what does that tell us about the nature of matter?
Right, so at the same time that these experiments are happening which break apart our understanding of sort of light and fundamental particles, we also have the discovery of radioactivity, Henri Becquerel, and then the Curies, and then also Ernest Rutherford, who was working in Cambridge as well. And between all these people, they start to understand that atoms are not necessarily eternal, right? That they have this inherent property of change over time and that they can transform from one type to another. And at first the understanding...
You mean like they can die in a funny sort of way?
In a funny way. Yeah. Well, if you define... Yeah.
Death?
Death is not
a good word because it's not living to begin with. But it changes.
It changes form, or it might change the type of atom or element that it was before. So
That's like alchemy. That sounds like alchemy, doesn't it?
It's exactly like alchemy. And in fact, they had to be very careful because it was very... alchemy is a very besmirched word in the scientific world, and you didn't want to be accused of doing alchemy.
Trying to turn base matter into gold, yes.
Exactly, yeah. And yet nature had been doing that for free all along. Right, nature had been changing atoms from one form into another all along, depending on their exact configuration of the particles inside them, whether or not that was stable or unstable. And so suddenly we get this shift in terms of, okay, nothing looks like we thought it did. Not just is matter unstable, but also around the same time they discover, or Ernest Rutherford discovers through a famous experiment called the gold foil experiment. Actually, it was his staff and student, Hans Geiger and Ernest Marsden, just to be exact.
Geiger as in Geiger counter?
Yes, Geiger
really?
is in Geiger counter.
Wow.
But this was the experiment he did before he came up with the Geiger counter. And some people say that it was his frustration of sitting in the dark counting flashes of light that led him to invent the Geiger counter later. But they discovered together that inside the atom there was no plausible way that it was just sort of a splodge or a pudding of matter all mushed together, that there must be a structure inside the atom that has a dense enough core that particles could bounce directly back off it.
Right, so the atom's not a smooth billiard ball, it's a plum pudding, as you say. It's got raisins and nuts and bits and pieces.
That's what they thought before. But then even the plum pudding model didn't hold up anymore because the results they were seeing in their experiments said, wait. And Rutherford described it well. He described it as like throwing a cannonball at a piece of tissue paper and having it come back and hit you in the face. It makes no sense. It doesn't seem like there's anything heavy or forceful enough inside the tissue paper to turn a cannonball around. And that's what it seemed to them doing their experiment with a very thin gold foil, was that there was nothing big or heavy enough inside an atom to turn an alpha particle it was around and send it back in the direction that it came. But that's exactly what they observed. And so from that, they formulate a new concept of what an atom looks like on the inside, which is a very, very dense nucleus that contains almost all of the mass, which we now know has protons and neutrons in it, but they didn't know that then. And then around the outside, the electrons in sort of a cloud.
And one of the most misleading things I ever experienced in science as a kid was that those wonderful atlases, and you open them up and you see the planets and you see the sun, and next to it is Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc. And they're really quite close together just to fit into the atlas. And that's... So it will fit on the double-page spread. And that, of course, when you're a kid, you think, there would be no bother at all to hop from one place to another. But, of course, the distance between the planets is impossibly huge. At the same time, we also got these little images of atoms with like a billiard ball nucleus with electrons sort of tightly whizzing around them. How off the mark is that little image of the atom with the spinning electron?
We now know, now that we understand quantum mechanics, which came out of all of this, that it's pretty wrong indeed, right? It's all kind of fuzzy, actually. But the dimensions is a very important point. So one of the best descriptions of this I've heard is that if you imagine that the nucleus of the atom is a fly, now place that fly inside a cathedral. The electrons are at the wall of the cathedral.
My God,
and
really?
And the nucleus is a fly,
Wow.
and it's the same dimensions. That's how small it is, but it contains almost all of the mass.
So does that mean that most of mass is empty space? That's us as well? Is most of us empty space?
Yes. Yeah. It's a bit mind-blowing, isn't it?
Sorry, this is a really stupid question, but why can't I walk through walls then?
That's the electromagnetic force stopping you right there.
All right. Okay, but nonetheless, it's still a wild concept, isn't it?
It is, and it really disturbed people, actually. Kandinsky, the artist, even wrote about how the crumbling of the atom, was like the crumbling of his soul, I think is how he described it.
He got over it.
I suppose he got it out in his artwork, didn't he? But it's quite interesting. If there was nothing holding that matter apart, you could take all of the particles inside all of the humans on Earth, right? And if there was nothing holding these things at some dimension, if there was no force between them, you could squish all the protons and neutrons and electrons down of all the humans on Earth into a space no larger than a sugar cube, which makes it seem pretty insignificant.
What effect was the discovery of this kind of knowledge? You were just saying at the start that science seemed pretty settled at the end of the 19th century. Suddenly we have X-rays so we can see human bones behind the flesh. We realise that there are particles within particles within particles that do different things, that the space between them is extraordinary like that. Was there sort of like equal parts tremendous excitement, but also at the same time the kind of thing Kandinsky's talking about, this sense of being terribly unsettled and sort of the world sort of thrown off its rocker?
Yeah, I think you've nailed it. I think there's like an incredible excitement coming, especially from the people who have the skills to research this stuff. Suddenly there's a new horizon opening up in front of them. And we haven't even got to quantum mechanics yet, right? And we now call the physics that emerged through this period modern physics, whereas we call what came before classical physics, because we have different word for it. It's so different. But among the general population, there was a lot of fear. For example, when X-rays were found, people were afraid. People were selling X-ray opera glasses, even though such a thing didn't exist. And they
I
were
used to see
banned
X-ray
from
specs
theatres.
in the back of comic books, yeah.
Right, and they were banned from the opera houses, even though they didn't exist, in case someone could see. And there was a fear that X-rays could see someone's soul. There was jokes and poems written about this stuff. And then, of course, there's the sort of existential crisis of, well, hang on, we're not even solid. We're not even solid entities anymore. And people start to ask those more philosophical questions about, well, what does all this mean, right? It's quite a fascinating and creative period.
So this is an era when, I suppose, science is a bit like rock and roll. It sort of comes along out of nowhere and overturns everyone's conception of what the universe is and what it's like. And this sense of being untethered maybe sort of comes into the culture. I think you can sort of see it in all sorts of ways, the new science, the effect it's having on the world, the introduction of all this new
like a shifting of our perception of both how the world works at its fundamental level, which is quite difficult to wrap your head around when that suddenly shifts beneath your feet, but also our role in it and how incredible it is that as people we have the ability to actually understand that.
This is Conversations with Richard Fidler. Hear more conversations anytime on the ABC Listen app or go to abc.net.au/conversations.
Photons. That's the next thing. Photons. There was a long discussion going on about whether a beam of light was made up, was a particle or a wave. And this is the time when this question gets answered. Tell me the story of how this question got resolved.
So it had been back and forth throughout the centuries, actually. People think this was a relatively modern discussion, but it wasn't. Our sort of philosophical conception of what light was made of did bounce back and forth. But once we understood electromagnetism as a force, which is through which you can write down the equation that shows that light is a wave that travels through space at the speed of light, and you can show that there's an electric field and a magnetic field and they're bouncing back and forth. They thought they understood light at the end of the 19th century. And then
who ruined it?
yeah, exactly. Once again, an experiment ruined it. So this sounds fairly disconnected, right? But there was two key experimental things that happened. One was that when you heat something up, it gives off light. If you think of blacksmith's forge or even a star, you sort of think, okay, the hotter the thing is, it might go from red hot to yellow hot to white hot. And the colour of the light, or the central colour of the light, shifts with temperature. We know they knew that at that point. What they couldn't do, though, was write down an equation which described why that was exactly. And it's called the black body spectrum. Just that's what it was called historically. And it's sort of an idealised shape of if I plotted the colour of light versus how much of each of that colour. Specific shape. They could not explain it theoretically. There were things that roughly got there, but not really. And then a theoretical physicist came along and came up with a way to fix that. His name was Max Planck. But in order to fix it theoretically, he had to invoke a very strange thing. He had to say that energy could only come in chunks, a certain size or larger.
Packets.
Sort of packets, yeah, which he called quanta. Now, this was a purely mathematical thing that he put in, and it worked, and it fixed the equation, and he was able to come out. But he didn't think that light itself, or the energy, the energy contained in a so-called chunk of light, he didn't think nature came in chunks, Like, he didn't think nature actually came in quanta or that light came in quanta. He just put this in and thought, well, it solves the problem. Okay, fine. Next, Einstein comes along and says, wait, there's an experimental result that I've been looking at out there. Now, Einstein was a theorist. He was not an experimental physicist. But lots of other people had been doing experiments where they shone light onto a plate of metal, and out of that metal jumped electrons or an electrical current which they could measure.
So what's pinging off that thing? Is that the question then?
No, it's which light will let the electrons jump out and which light will not let the electrons jump out. And Einstein came up with a theory to describe this. It's called the photoelectric effect. So photo being the light and electric being the electricity it gives off. And no one could really describe the experiments well theoretically. And he came back and said, well, actually, if we take Max Planck's quanta thing and we treat it as being real and we treat light as chunks of light as quanta, then we can predict that actually below some frequency or some colour that's sort of further down in the spectrum, no electrons will come out at all. No current will flow at all. And that doesn't matter how bright that light is, no electrons are going to jump out because it's beneath this sort of energy threshold. And everyone was like, well, this is a, I think it was called like an irresponsible hypothesis, right? Something like that.
Einstein was doing an irresponsible.
That's right, the reckless hypothesis it was called.
Right.
And so now, we turn back to the experimentalists, and there was an experimentalist in California named Robert Millikan, and he spent 12 years in his laboratory trying to do this experiment well. And sometime into that experiment, Einstein's theory comes out. And then he turns back to his apparatus, upgrades it again, and now he's like, right, I'm going to disprove Einstein. Because he does not believe, just like nobody else believed that the universe came in chunks or quanta, right? Let alone that light was made of chunks. We all knew it was a wave because the wave theory predicted everything beautifully. So there was no way, he thought, I'm going to do this experiment. Surely it will be able to be explained in some other way. We won't need Einstein's reckless hypothesis.
So he spent 12 years trying to disprove Einstein.
And you know what he did? He proved Einstein more right than anybody had before ever.
Did he admit that though?
He changed his story. So his experiments finished in about 1916, and he got the 1929 Nobel Prize for that and another measurement that he did.
Right. Well, it's nice he got a look in, isn't
and
it?
And by then he changed his story, right? And he said, oh yes, when I set out to measure, Einstein's theory of the photoelectric effect, and it was actually Einstein's theory for that effect that Einstein won the Nobel Prize for. It actually wasn't for his more famous relativity. But so we start to get, through these early experiments and the interaction with the theoretical physicists, we start to get this idea that nature is not working how we thought it did.
So we end up with this idea that, well, this reality, I suppose, which is that light is both a particle and a wave.
Exactly.
That seems to defy common sense. And I just don't, again, that's like the 100,000th thing that's ever happened, I think, in physics that seems to defy common sense, that works into all your models of reality. What? How can it be a particle and a wave? Is that even a good question to ask? I don't know.
In some circumstances, when we measure it, it has particle-like properties. And in some circumstances, it has wave-like properties. So, if I shine a torch through a prism or a lens or something, then I can predict pretty well what's going to happen based on the wave-like nature. But at the end of the day, light is just light. And all these models that we come up with and all these common sense things we come up with, all these pictures in our head, are just trying to describe a phenomenon in nature. So it's actually, I would flip that around and, that doesn't make sense. And I'm like, well, hang on, nature has to make sense. It's just nature.
So this is why you and other physicists are shy about these tight definitions I keep trying to trying to thrust upon you then. So
because we're trying to open our minds and be like, how does it actually work? And if you're like, right, but is it this model or this model? I'm like, I don't know, it might be neither.
I just want definite answers, and it's like trying to ask, the physicist will always go, well, and then you get an answer.
Slippery like a photon. Yes.
slippery as a photon. So we have here a tiny not a fundamental, but a tiny particle that's not an atom, and it's outside of an atom as well. And then we come to cosmic rays that exist outside of atoms entirely. What are these particles that make up cosmic rays, and where are they, and what are they doing right now?
So this I think is one of the wildest facts about nature, that most people, even when we think about atoms and particles and things, everybody thinks of the particles within what we would normally call matter, the stuff around us. But when I say matter, I actually mean any sort of particles. And cosmic rays are a type of matter. It's just that they play no role in our everyday matter. So they play no role in atoms. And they were found originally in the early 1900s because people observed that there was some sort of extra radiation in their detectors. And eventually a guy called Victor Hess goes up in a hot air balloon with a radiation detector and manages to establish that there is far more of this radiation high up in the atmosphere. He goes up to about 5,000 feet, I think, which is incredible in those days. And he manages to measure that the amount of radiation increases as he goes up, whereas they thought the radiation was coming from the Earth, from the minerals in the Earth. So this was a complete surprise that actually there's extra radiation and it must be coming from outside our atmosphere, coming from outer space. And he did a quick experiment to test, is it coming from the sun? And the answer was no. It's really coming from further out in space. Now, there's a whole spectrum of different particles. There's the gamma rays, which are high energy light. There's high energy protons, which are a lot of the cosmic ray spectrum, and then they hit our atmosphere, and then they can create all kinds of other types of particles.
Sorry, when you say rays, though, cosmic rays,
Yes.
that does imply it's being radiated from something, doesn't it?
Yes, the problem is we don't know what.
We still don't know?
Still don't know. There are mechanisms out in space, in astrophysical objects, that can, in a magnetic field or something, that can speed up particles out, around a black hole or around some other stellar object, or even in the early stage of the formation of stars, that might throw off, or even in a supernova, that might throw off high energy particles that might travel across space to us and come to our planet as part of the cosmic ray spectrum. But some of these particles we've now discovered have so much energy. I mean millions and millions times more energy than even we can create in the Large Hadron Collider. And they're raining down on us from space all the time, and we actually don't fully understand the mechanism of how they reach such enormous energies still.
And are they coming down like in a single stream, or is it like a bazillion flashlights pointing from different directions? Are they sort of smashing into each other, or what are they doing?
It's kind of like just a bath, right? Like it's
bath.
just like there's just
it's like soup or something. Is it flowing, or is it more like a static thing?
Well, it doesn't change too dramatically in time other than the solar flux. There is some coming from the sun, and that does vary over time depending on the sun's cycles. And because a lot of them are charged particles, they'll vary a little bit with the Earth's magnetic field and things like that. But generally, it's just this huge flux of particles coming towards and through us all the time, and we are completely unaware of them.
Right.
Through us.
So these are the ones that don't ping off the atmosphere, the upper levels of the atmosphere. These are ones that
they don't generally ping off. They'll come through, they'll interact in the atmosphere, and then there'll be a shower of other particles that come down onto us.
Right now.
Right, yeah. So if you held out your hand...
I feel fine.
If you held out your hand... Yeah, there's sort of a few going through your hand every minute of the type which are called muons, which are like heavier versions of the electron.
When you say heavier, that's not very heavy though, is it?
About 400 times heavier than the electron, so not hugely heavy. Mm-hmm. But they, we didn't know about them. Before it was 1936, I think, that the muon was discovered high on a mountaintop using a type of detector called a cloud chamber. And they play no part in atoms whatsoever.
They don't, right. What does that mean? They just pass through the space of the atom, or they're just too tiny to affect it? Or, I mean, what does that mean?
They don't. What I mean is we don't form atoms out of... So if the muon is a heavier version of the electron, you could almost imagine a type of atom that existed that was very heavy that had muons around the outside instead of electrons.
So when you say they're passing through our bodies, and are they like just we're going back to that old cathedral metaphor you used? Are they just like a tiny insect flying through the cathedral window that just doesn't even come anywhere near it? Or is
they're tiny. Yeah, they're tiny, and often they have high enough energy that they're barely going to interact with us, and they would only deposit a tiny amount of energy as they go through our body. But we do have detectors now that means that we can actually observe them. And one of the most ingenious types of those detectors is called the cloud chamber. It was a very early type. They're
like
beautiful.
Storms inside a box, aren't they? That's what they look like.
It's like miniature contrails, but the contrails are formed by these invisible particles. And being able to actually visualize them for the first time taught us a whole lot of things about how these different particles interact and how they all fit together, because suddenly we weren't just asking what's inside the atom, what's our matter made of. Suddenly a whole lot more questions opened up. It's like, wait, hang on, there's radiation coming from space, there's types of particles that we didn't know existed before, and before we even got to the muon, by the way, they discovered antimatter. So they discovered the positron, which is exactly like an electron, but has a positive charge. And if it comes in contact with an electron, it annihilates.
They annihilate each other?
Exactly.
I didn't even know how that can be in the world either. That's just kind of, it's like, where did they both go? I mean, they pop in with the universe or what?
It's actually one of the foundational questions of the universe that we're still trying to answer. It's not quite why antimatter exists. Our theories say it should exist in equal quantities to normal matter. And one of the big mysteries that we have still to solve is why do we see around us almost all matter and barely any antimatter?
There's some cosmic junkyard with all the antimatter in it somewhere lying around.
Not that we've seen. But
that we've seen. So, and this all brings us to the neutrino. Is that one of these, the neutrinos, in some ways the most enigmatic and mysterious of all these little tiny subatomic particles?
It is.
Is this one of these cosmic ray particles?
Yes, they can. So neutrinos can come both from the sun and also from elsewhere. They're often produced as atmospheric neutrinos, so those interactions from protons protons in our atmosphere produce not just the muons, but they also produce these neutrinos. Now, just for people who've never heard of a neutrino, it was originally thought to be a completely massless, like the photon, like light, neutral particle, which just happens to need to exist theoretically because it solves a problem that we had with beta decay, one of the early discovered types of radioactive decay. Now, that doesn't sound like a very good motivation for a particle, right? Oh, okay, it solves your mathematical problems. But it was quite highly motivated. But it took more than 50 years for someone to actually bother to go after it and try and detect it, because it barely interacts with anything.
You mean it passes through the Earth?
It passes all the way through the Earth and out the other side. Now, muons don't interact much. They can pass through sort of meters of rock. But a neutrino is so small, and we now know they have a tiny, tiny mass, but so small and so weakly interacting that it can pass through, I think the number is actually light years of lead.
What do you mean, a slab of lead that is light years thick?
It's just ridiculous.
Are you saying a neutrino is a particle that would, with a tiny bit of mass, that would pass through a slab of lead that is a light year thick?
Yes, but they're so weakly interacting, and so for us to detect one in a detector, they ended up having to build like these enormous tanks of liquid that the neutrinos interacted with, and it was like this almost farcical experiment that they did. And I think they found in the first instance about 5 neutrinos after decades of work to do this. It's just incredible that the energy that people poured into this thing, which may or may not even exist in the universe.
So you're an accelerator physicist, is that right? Which means you specialise in these new technologies that you write about in your book, about these particle accelerators that essentially, correct me if I'm wrong here, they're both like a gun and a merry-go-round at the same time. They sort of fire these infinitesimally small particles like bullets into each other. They shatter and they break open and you see what's inside. Is there some kind of weird inverse law of proportionality to this, Suzie? Because it seems like the smaller the particle you're looking for, the bigger the machine needs to be. And so now we have the Large Hadron Collider, and I think there's something else in the works at the moment too that's even bigger still.
So there's a couple of different aspects to that. So the particle accelerator itself just is designed to just give the particles energy and get them up to speed. Once we're doing that in opposite directions and smashing them together, then I call that a collider, which is most of the big particle physics machines, like the Large Hadron Collider. And then when we say this sort of law of proportionality of are we looking for smaller and smaller things, we're not technically looking for smaller and smaller things.
But that's the way
in
it's
terms
panned
of
out,
dimension.
isn't it? I know.
We're looking for rarer and rarer things now. And so we have to have sufficient energy to first create those particles. And physical dimension is no longer that useful indicator. What's useful to us as physicists in that is the mass of the particles that we're looking for, because heavier particles are much more difficult to create. So we need the higher and higher energies to create heavier particles. So for example, the Higgs boson that was found almost exactly a decade ago has a mass which we use even in energy terms, because we have this equivalence of about 125 million electron volts of energy, which is heavy. That's the only context you need.
So to use a really coarse metaphor, it's not so much the size of the bag of chips you're looking for, it's the weight of it. It's the mass of it.
And how rare it is, and how rarely it is created when you smash protons into each other, for example.
2012, they discovered the Higgs boson that was theoretically a thing. They needed it to exist, and then it turns out it does exist. This is what the Large Hadron Collider discovered. It was called a God particle at the time. Why was this discovery so important, Suzie?
So in about the 1970s, they got to the point where they had a list of something like 208 different particles which they thought were fundamental. Or a little bit earlier than that. They had early 1960s, let's say. And from there, what happened is we had to put together a theoretical model, which we now call the Standard Model of Particle Physics, which is quite an incredible feat of ingenuity over many decades of work, which is to understand what is actually fundamental within those 208 particles and what is actually just taking different pieces and putting them together in different combinations. So we now understand in the Standard Model of Particle Physics that there are particles called quarks, and there's 6 different types of quarks, and they fit together. Only 2 of those go into our normal matter. The proton and neutron are made up of quarks called up and down quarks. That's it. And then there's what we call the left, so the electron and the muon that I discussed, and there's an even heavier version called the tau. And then they all have neutrinos associated with them. So we're building up a building block now of here's all the fundamental pieces, and they interact through different forces. And explored those different forces. But all of those particles in the theory had a mass associated with them, a number associated with them that gives them that mass. And the mechanism to generate that theoretically was this so-called Higgs mechanism. And that theory predicted that there should be this heavy particle called a Higgs boson, but we'd never observed one before. And they'd been trying at the machine prior to the Large Hadron Collider called the Tevatron, which is a brilliant experiment, and they'd been searching for that after they'd discovered some of these other heavier quarks and things. Brilliant run of experiments, and they didn't quite get there. And so the baton sort of passed to the Large Hadron Collider when that started up, and eventually in 2012 they'd gathered enough evidence to say beyond doubt that this particle does exist, and that meant that that whole theory sort of hung together and can predict things to like 9 decimal places.
So at last something reassuring from an experiment. But let me ask you this, like it was determined that the Higgs boson couldn't be observed in the wild, it had to be created through a collider. Why couldn't it be observed in the wild? Was it a sense of its scale, or how long do these particles live for when they appear in the world?
So they don't live very long. So tiny fractions of a second. And
really, they just flash in and out, do they? That's just like bing in and out.
So one of the key things is when something is heavier and unstable, it has a shorter lifetime. So a Higgs boson, which is quite heavy, lives almost no time at all before it decays into other particles. And it's those other types of particles that they're detecting at the Large Hadron Collider and then sort of tracing them back to say that one came from a Higgs boson.
I know it's much messier than this, and please, let's just take that as a given, but it seems like this whole process has been like a tightening of the microscope, or I suppose opening Russian dolls. You have the atom, and that idea of that being the fundamental particle was around for a very, very, very long while. It turns out the atom's made up of protons, neutrons, and electrons. Then it turns out that the protons, neutrons, and electrons are made up of quarks. And now you're telling me that the quarks are made up of even smaller particles. And it seems like
we haven't found anything inside quarks yet.
All right, okay. But it seems to me like at each stage, like, you mean there's something more? And it's like physicists seem to be shocked by this. Is there an expectation that there is some kind of basement level to reality to all this? Or is it, it's like, Richard Feynman once said, there's plenty of room at the bottom. Is there, the universe is infinitely big. Can the universe be infinitely small as well, is the question I'm asking. This is a philosophical question.
It is. I was going to say, it's much more of a philosophical question. And I think if you were entering the field of physics today, that your stance on that question would probably determine which field you end up in, right? So, for example, I looked at that question eventually and then I went, well, we went down in scale, right, inside the atom, inside the fundamental building blocks of the atom. And then what we actually discovered was something unexpected. We discovered there's all this other stuff other than atoms. And then we're looking at these different fundamental particles and different forces. And now, through this connection between fundamental particle physics and our understanding of, say, the evolution of the universe and cosmology, we can now, the theoretical physicists, of which I am not, are now starting to understand that all these pieces fit together. So our understanding, for example, of the tiniest building blocks of the universe help us understand how our universe has evolved into the way it looks today, which always blows my mind that there is this intricate connection between the largest and smallest scales of the universe. And it kind of looks now from the outside like, okay, you found the Higgs boson, particle physics is done, right? Doesn't that remind you of a phrase we used at the start of the interview?
So at the end of all this, there's another question I want to ask you. You know what? Oscar Wilde once said that one of the most vulgar questions you could ask of art was to ask what it was useful for. Science, I mean, you're a great defender of just pursuing science for its own sake, for sheer curiosity's sake, and I think that's brilliant. I completely agree with you. Nonetheless, when people say, well, this is all very well, you looking for these little things, but what use has it been? What are the kind of things that have, the little kind of byproducts that have come from this research into the nature of matter, Suzie?
It is almost too large for people, almost too many for people to wrap their heads around. So, X-rays were being used on the field to detect shrapnel in people's bodies within a year of them being discovered. And now, if you are rushed into hospital with a stroke or anything like that, first thing you do is a CT scan that's based on X-rays. We had the understanding that atoms are unstable has given us things like the ability to date things through radiocarbon and radiometric dating to understand not just the full history of our our Earth and our species, but also how those things change over time, and the age of the Earth itself, right? And how that fits into our universal scale. All of the electronics industry came from these kinds of experiments.
Yeah, you don't have electronics without electrons being discovered, do you?
Precisely,
Right, yeah.
exactly. And our current electronics would not work if we didn't understand quantum mechanics, let alone the next generation of electronics and quantum computers. Nuclear power, of course, there's things which have been taken out of the hands of physicists and used for evil, not for good, in the nuclear realm as well, which is not the journey I'm on. But then almost all of our modern high-tech medical technology comes from this field. So radiation therapy, the treatment of cancer, in half of all cancer cases, uses a particle accelerator. You can even get to the point where we're developing things like the World Wide Web. It's almost endless.
The accidental byproduct of all this particle
Exactly.
research. How brilliant. What an amazing story. Thank you so much, Suzie. Accelerator physicist Suzie Sheehy is the author of The Matter of Everything, 12 Experiments That Changed Our World. I'm Richard Fidler. Thanks for listening.
Hit subscribe for more, or try out the ABC Listen app for thousands of other podcasts, all ad-free.